Hello there, my name's Richard Arundal and thank you very much for taking the time out to watch this video. So this is the first of hopefully many different MATLAB tutorials that involve spacecraft engineering principles, and today we're going to be looking at the Hohmann Transfer. So if you like what you're hearing and you like the video, then hit that thumbs up button and subscribe to the channel so that you can see when new videos get released. So in this video we're going to have a look at some of the theory that's required to calculate a Hohmann transfer, and that includes some of the gravitational parameters and some basic orbital mechanics. We're also going to combine this into MATLAB, which is the main focus of this video, and we're going to use a graphical user interface that I've built, and I will share as well the MATLAB code that I used to create this calculation. And then we're going to top it off with some more formal book references so that you can have a look at the books yourselves and perhaps get a copy and other ideas for your own programs. So let's start off then with some background information with the law of gravity and the theory behind it. So the main takeaway that we want from this slide is the universal gravitational constant, which is the capital G letter, and we've got our value there. And that is what we're going to use in the Hohmann transfer calculation shortly. Now the rest of the slide is more background information, and by all means please stop the video here and take the time to read it, but for the Hohmann transfer it's not necessarily required at this stage. The next important parameter that we need is the gravitational parameter, mu. And this is fairly straightforward, and it uses the universal gravitational constant G multiplied by the two masses in question, as in, let's say, a planetary body and a satellite. It's their masses, so m1 plus m2. Now when we consider artificial satellites and spacecraft, m2 is negligible compared to the mass of the planet, so it simplifies to universal gravitational constant G times the mass of the celestial body. Now we don't need to calculate these because these have already been calculated for many celestial bodies and they're included in the table that's on this slide here. So the final bit of background theory that we're looking at is a bit of geometry which we use to explore and design orbits, and this is the concept of periapsis and apoapsis. So the periapsis is the minimum focal distance and the maximum distance is called the apoapsis, and we can see that in the diagram at the bottom of this slide here. Now depending on literature or mission parameters, the apoapsis and the periapsis may have different names, and they derive from the classical history and Greek and Roman gods, as many of the planets are named after them. So you could see alternatives for perigees and apogees, for example, would be talking about Earth, or perigove and apogee would be talking about Jupiter related orbits. So if you're reading literature and you see the second part of the name different from apsis, that just means it's talking about a particular planet, and the table here will show the counterpart names for your reference. So the first slide we're going to look at here for the Hohmann transfer theory is the algorithm that we use to calculate it. And the Hohmann transfer itself is a two-impulse maneuver for transferring between two coplanar orbits that share a common focus. Now this could be thought of as a change in altitude of an orbit, and there's three orbits that we need to consider, and that is the starting orbit, the transfer orbit, and the final orbit. And the next slide coming up will be representing that diagrammatically. The algorithm itself then makes use of calculating angular momentum of the orbits, orbital speeds, change in velocity, and as an option we can also calculate the mass of expended propellant for the entire transfer. So please feel free to pause the video here to read through the transfer algorithm that I've got up on the slide here, and then we'll progress on to the diagram of the Hohmann transfer itself. So this is a basic diagram of what a Hohmann transfer actually consists of, and working from left to right then, we start off with the original orbit, which is the green dotted line, And assuming here this is a circular orbit, but it can also be highly eccentric, that is absolutely fine, because then that just means your apoapsis and your periapsis are different. So we start off with that orbit, but then we decide that we want to transfer, in this case, to a higher orbit. Now bear in mind this also works the other way, that you can go from a higher orbit to a lower orbit. But for now, let's stick to what we've got on the slide here. So the first orbit is the green dotted line that circles around the origin or the planetary body, let's say. And what we want to do is, in order to enter the transfer orbit, we need to carry out a orbital velocity change. And in this case, because we want to achieve a higher altitude, we need to increase our velocity. So the first velocity change there we can see on the second from left diagram, and the transfer orbit then is the blue dotted line, because as the satellite speeds up and you've got the propellant burning, the orbit will change and we will achieve a higher altitude. So that's the transfer orbit. But then once we get to the desired altitude of the final orbit, we start looking at the third diagram from the left here, where we can see we're approaching the red dotted line. Now if we do not carry out an orbital change here, or a burn or an apogee kick as it's sometimes called, then that blue trajectory will continue, and that will be the orbit that the spacecraft will achieve. But if we want to remain in this third orbit, the final orbit, we need to carry out that second velocity change, which in this case we want to slow down the spacecraft so that we can remain in this orbit. So that's where the second orbital change comes in. And then once that's achieved, we then achieve the final orbit on the right hand side, which is the red dotted line and circle. So as I said before, this can be reversed as well. If we wanted to go from a higher altitude to a lower altitude, what that would mean is that the delta V, or the velocity change, in this case would be to slow down the spacecraft so that the transfer orbit would drop into a lower altitude, and then a second velocity change would be required to correct the orbit so that it maintains it at that lower altitude. And that is essentially the basic theory of the Hohmann transfer. So to calculate the Hohmann transfer, what we need is to know the angular momentum, the orbital speed, and the change in velocity, or the delta V. Okay, so on this slide we've got the equations here so that you can calculate the angular momentum, the orbital speed, and the delta V. And what we do is repeat this for each stage of the transfer, and this will be a lot more clearer when we come on to the MATLAB GUI in a second. So by all means, pause the video here, have a look at the equations, and we'll move on to the final set of optional equations if you want to work out the propellant on the next slide. So to calculate the amount of propellant that is used up during a manoeuvre such as a Hohmann transfer, we could use the equation that's now up on the screen, which basically is used to determine the amount of mass change, as in the propellant used. Okay, and we do a little bit of transposition of formula later on, but what we need here is basically m is the mass of the spacecraft. The delta V is what we calculate, the total delta V from the Hohmann transfer, so we'll know that shortly. The ISP is the specific impulse, which is to do with the efficiency of the rocket that we're actually using to use the propellant and carry out this manoeuvre. And G is the gravity of the celestial body that you're orbiting. So if we're looking at Earth, for example, that would be 9.81 meters per second squared. So if you wanted to take some time now to pause the video and read through the text that's up on this slide, please feel free to do so. And after this, we will be moving on to the ISP and actually looking at the MATLAB GUI and the code. So take your time, and we'll see you on the next slide. So here are some examples of specific impulses. Now, a specific impulse is basically a measure of how efficient a rocket uses the propellant that's part of the system. And what we can generally see is that the lower the ISP, the specific impulse, usually you get a much higher thrust, whereas the higher the ISP, which is very efficient, you don't tend to get as much thrust. So when you see the big rocket launches taking satellites up into space, they will normally use propellants that are very low ISP but generate the enormous thrusts required to actually get the launch vehicle up into space. So finally, in this presentation, we get to the slide where we can see the graphical user interface, or the GUI. And this is one that I've created myself using the MATLAB Application Designer tool. And I personally find it very intuitive and easy to use. And there's lots of great tutorials on YouTube to actually show you how to develop this. So I'm not going to reinvent the wheel and necessarily show you how to use the app designer, although of course if you feel that would be something that would benefit you and you'd like me to go through it, leave a comment below and let's see what we can come up with. So in this GUI then we can see that all the different parameters that I've talked about in the previous slides, and the little white boxes on the left hand side for the altitudes of the starting and final orbit can be edited. And then the grey boxes on the right hand side are mostly calculations with the output come out. So we can see here that the 3 angular momentums are calculated. So are the orbital speeds and the required delta V at the different points. So we've got the delta V at point A in this example is 1.422 kilometers per second, and the delta V at point B is 1.139 kilometers per second. So the total delta V for the entire transfer in this case is 2.561 kilometers per second. And the nice thing using a GUI like this is you spend a little bit of time as the developer actually building the program and inputting the calculations and making it user friendly, but once it's built, very easy to use, and you can amend the numbers and it'll update and recalculate as required. And let's not forget, of course, at the bottom here we've got the propellant parameters and results, so you could put in the mass of your spacecraft, and if you know the specific impulse of your propulsion system that's going to carry out this orbital maneuver, you can put that in as well and work out the kilogram value of expended propellant to carry out that transfer. So it could be very useful when you combine all these different equations together in a simple and easy to use tool. So this final slide then for the MATLAB code part is all of the text that I use as part of the GUI, and it's assigned to the calculate button. And I haven't put all of the code from the GUI itself because a lot of it relates to the different buttons and the labels and so forth. But this is the core of this particular application which carries out the calculations. So I've got it up there for you, and what you can do, you could pause this video if you wanted to look at it in more detail, or if you wanted to copy it perhaps in your own MATLAB programming. What I do want to do, however, and it might be a little bit after the time of publishing this video, which is February 2021, I'm going to actually add this to my website on www.arundalastronautics.co.uk. I've got the link down below in the description, and what I'm actually going to do is make this free and open software so you can actually download it and have a look for yourself. Maybe you could look at it and go, I've got a much better way of programming that's way more efficient, or maybe there's other things that you could add, or perhaps you're an engineering student and this would be useful in your own studies, that you don't have the time to program something yourself. So by all means check out the website below, and hopefully by the time you are watching this there'll be the download version that you can have a play around with yourself. So pause the screen here if you want to have a look at the code, or check out the website and download the program for yourself. So let's finish up then with some book references that I've used to support this presentation. And if you want to see more references for your spacecraft engineering textbooks, by all means visit my website with the link below, and I'll also put an actual URL link in the descriptions of this video, and check it out. See if there's anything there, or if perhaps there's a book that you have that I've not listed up there. Let me know and I'll get it up there, and I'm all for promoting different bits of literature and supporting the spacecraft engineering community. So I'm going to end it there, and thank you very much for watching this video, and take care, and I look forward to presenting the next MATLAB video.